Picture a 10 GB server log. Somewhere inside that massive text file is a single malicious zero-day vulnerability. To stop the breach, the system has to find a very specific footprint, perhaps a 50-character string of rogue code. The most intuitive way to look for it is a brute force naive search. The computer takes the first letter of the log and checks if it matches the first letter of our target code. If it doesn't, it moves to the second letter. The trouble starts when things look promising. The computer reads the first 3 characters and they match perfectly. But then, on the 4th character, it hits a wrong letter. A near match forces the CPU to spend its maximum effort checking multiple characters sequentially, only to throw the entire result away. After that failed match, the computer shifts its focus forward by exactly 1 letter. It completely forgets that it just spent time verifying the previous 3 characters and starts the entire matching process over from scratch. We express this repetitive work as big O of n times m. You multiply the total text length, n, by the target pattern size, m. If that log is filled with near matches, this grid balloons, resulting in hundreds of millions of redundant checks. Algorithmic traps, rather than hardware read speeds, create the most severe bottlenecks in massive data processing. To escape this bottleneck, we must move away from comparing individual letters and start comparing numbers. This is where we use hashing. Running our target strung of code through a polynomial equation generates a single, compact numerical fingerprint. We then pass the first 50 characters of our server log through that exact same equation, generating a second numerical value. Comparing an array of 50 letters takes 50 distinct computational steps. Comparing 2 integers takes a CPU exactly 1. Hashing converts string matching from a structural comparison problem into a simple mathematical equivalence test. But if we have to recalculate that mathematical equation from scratch every time we move forward 1 letter, we haven't actually saved any time. Rabin-Karp solved this with a rolling hash. Sliding forward, the algorithm drops the exiting character's value and adds the incoming one. Computing only the difference executes in constant time, requiring the exact same effort for 5 characters or 5,000. Because numbers are finite, eventually 2 entirely different strings of text will mathematically evaluate to the exact same hash value. So when the algorithm finds 2 numbers that match, it hits the brakes. It performs a quick character-by-character check to verify the hit is genuine and not a coincidental mathematical collision. The algorithm accepts a tiny bit of occasional verification work. In exchange, it mathematically filters out 99% of the data stream at lightning speed. Running this rolling hash through our 10 GB server log, the search glides over millions of characters and locks on to the zero-day footprint. By eliminating those nested loops, the worst-case time complexity of n times m collapses down to a highly efficient n plus m. What if that server log isn't just threatened by 1 vulnerability, but by thousands of different malware signatures at the exact same time? Because the text is already converted into numerical fingerprints, that single sliding window can be checked against a massive dictionary of target hashes simultaneously, in 1 single pass. This mathematical scaling is how global software compares essays to billions of articles, aligns complex DNA sequences, and automates global malware audits. In computer science, achieving true speed doesn't require a machine to read faster. It requires engineering the memory so the machine never has to do the exact same work twice.